So we are expecting that participant should be here by maybe 50. Anyway, we can start our schedule tutorial.
Okay.
Okay. So floor is yours.
So the first one is dedicated to exergy and energy evaluation of solar hybrid photovoltaic thermal collector, and especially also with phase change materials. Why is it a good example of using exergy? Is because we have two kinds of energy. It's the same unit, but it's not the same content. Okay. With electricity, you can do what you want. You can heat, even you can heat a boiler, just injecting the electricity by a resistance. Okay. You can cool, couple with a cooling machine. You can have light. You can do what you want. So the content of 1 watt of electricity is different of 1 watt of thermal energy. Thermal energy can have also a good potential if the temperature is at a certain level. We have seen that we are able to generate what we want if we concentrate the solar energy and if we reach a temperature over 200, 300, so we are able to generate steam. Then from the steam we are able to generate electricity, or we can generate heat, we can generate cool. We will see in the lecture about solar heating and cooling. Okay, so the content is not the same. So if we want to, if we have a system which is doing both, we should be able to add a kind of unit, so to clearly highlight what is the energy potential of this component, which is mixing thermal and electricity. So it is exergy. We will see that later. So the origin of PVT, I already show you the spectral solar spectrum. After he has crossing the atmosphere, so you see some hole here due to H2, so absorption. You have also azote absorption and CO2 absorption, and so on. Okay, so the first is say, okay, the only part which is useful for PV is in short wavelengths, and most of the energy coming from the sun, so around 80%, is not unanswered, is not used. Okay, so is it possible to try to use a part of that using the PV collector as a collector also for thermal? Okay, so it's the first thing. So there is different family of hybrid photovoltaic thermal collector with air, with water, covered or not, with also concentration. This is an example of concentration CPV. Here you have the PV cell, okay, and you have concentration of solar radiation on this focal. So at that stage you are also collecting solar energy for PV conversion, and also at the back side thermal energy that could reach for such components more than 100 degrees. It could be oil, for example. Okay, this is we can see it seems to be a PV function, uncovered, okay, because we don't see a glass over the PV module, so it looks like uncovered hybrid photovoltaic thermal collector, probably with water, because uncovered can't reach high level of temperature. Okay. With air, there is different, you can find in the literature different way. So you can have a glass cover and at the absorber level layer of PV cells. Okay. And so the air, just a disconnection. So the radiation is crossing the glass, go to the cell, a part is converted in electricity, and the other part is recovered as thermal energy on air. So on Q, M, C, P, delta T, T out, 1, T out. So it's allowed to hit the air. As it is glass covered, you can reach 50, 60 degrees on air. Okay. So it could be for drying, for example, when you need some heat on air. So it could be useful for drying and so on. Other solution is to have the PV as a cover. Okay, so a semi-transparent PV that allow in some part to leave the radiation crossing and the part which is absorbed, converted in electricity. So finally you could be heated in both sides, but in this configuration the level of temperature is lower than here. Okay, you have other configuration, double flux, one at the upper face or the out face, or to increase the path of the air and in a loop at the which is the case, for example, with evacuate tube water. With water, you can have a circulation like this around the absorber. Okay, so it is with air, which is the more simplest way to recover a part of it, but of course the heat mass of the air is less efficient than heat mass of water, so you are recovering less. So example. So this is an example also that we have developed in the past on a project where the principle was to have an operating principle during the summertime. Okay, so during summertime it is a double skin with PV envelope. Okay, this is PV. And so during summertime you use this PV envelope as an absorber.
So what is the objective here? Minimize?
To heat, and so you try to develop the natural ventilation by chimney effect. Like this, you generate a free cooling of the PV envelope, and you can also use this kind of natural ventilation for ventilated inside the building. Here you have the north, here you have the south. Okay, so the cool air is in north where there is no sun and cross. Okay, during the winter time we want to use it as a solar hybrid photovoltaic thermal collector. So it is closed, there is closed and so we recover a part of the preheating of air with circulation. So it's a kind of trombe wall. developed in the 1970, something like this. Okay, so you collect, so you use it evaporating the air of the thing. So it's mechanical, of course. Here you have obliged to ventilate, whereas here it's natural convection. So this is an example of BIPV-T or BIPV with T. So this is what we have achieved for, it is experimental dwelling house. So it's a double skin PV facade. As I showed you yesterday, we were playing also with the color of the sails, just playing with the anti-reflective coating. So changing the width of this anti-reflecting coating. You can notice also that there is a difference of density of sail for some modules. So not here, it's fully opaque, but here. The principle is to leave some light going inside the house and to concentrate the sail when there is solar spot in summertime. So it is to protect the building to overheat. Thanks to this protection, we have modelized the solar radiation path, and at the place where during summertime there was a more concentration of solar energy, we put more cells to protect. Okay. But for this kind of configuration, in terms of inverter, if you have followed my lecture this morning, what you have to do, is it one inverter for the whole installation? Is it one inverter for the roof and one inverter for the facade? What you will do?
Inverter cost is also very high.
Yes, the cost is very high.
We need to check with this.
So you can have one inverter for that, okay? Seems to be uniform, opaque, and so on. But for this, it's a kind of mismatch, because each module has a different power, okay? So it looks like if in some modules there is shadow, because there is no cell, okay? So for this, you are obliged to put one microinverter per panel, okay? Because otherwise it will be completely randomly. So for this configuration, it was the beginning of the microinverter. So there was one microinverter per module, because there was such a difference of power between modules that it was impossible to manage. Okay. So for this, for sure, when you see that there is one microinverter per module, this could be one inverter for the whole. And even if it was uniform here, okay, even if it was uniform here and uniform here, you are at least obliged to have two inverters, because even if it is the same panel here and the same panel here, the inclination is different. So they will operate in a different condition, okay? So you can't put, even if it was fully uniform, you can't put only one inverter for the whole installation. You have at least to have one inverter for this part and one inverter for the roof. Okay? It's a double inclination. We have developed also other hybrid photovoltaic thermal with water. So the first attempt was a long time ago with glass covered. We bought a solar thermal with copper heat exchanger, and so we put some conductive past and put the solar PV and then a glass cover. It was not so good at the time, but we could reach, in terms of efficiency in electricity, between 10 and 15%. The more accurate that we have developed, it is this one. It has been developed with EDF and the Fraunhofer Institute. It is a glass cover PVT. So finally the configuration is like this plus a cover. Okay. The innovation is that the PV cell were directly put on the heat exchanger. So there was no backsheet, only a film in order to protect the cell from water, but no, so it was directly put on this. So it was quite efficient, but it is glass cover. So for this kind of PVT, you are obliged to manage the production of hot water. That means that we were able to reach 80 degrees with domestic hot water. We could reach 85 degrees. Okay? So that means that if you reach with water 85 degrees, you reach with your cell not far from 85 degrees. So it's not good for the PV function. Okay? At the beginning, there was a lot of damage because there was dilatation. Some cells were cracking. The silver part was sometimes also cracking and so on. So for such a collector, you have to manage few hours in the day to produce hot water for domestic hot water, and then you have to give the priority to electricity. So that means to have to use the water to cool and not to increase in temperature. Okay. It is the reason why that you don't really find industrial application of such components, because it is too dangerous for industry to sell such a kind of covered hybrid PVT, because in terms of warranty, insurance, you can imagine that if the temperature is growing too much, for example, when people are going in holidays, they don't use hot water, the temperature could increase and destroy completely the PV function. Okay? And even in time, in terms of aging, if one time per day you reach 85 degrees for 2 hours, it's not really good for the PV function. Okay? So this is the reason why that it was very efficient, but very hard to manage and difficult to find in industrial level, because in terms of warranty of performance in time could be
In the life of the PV cells.
yes, of the PV function, and all the PV connection don't like too much. So we also work with this company, which is Dualson, which manufacture industrially in France PVT uncovered. Okay, so the principle of a heat exchanger were more or less the same without cover, and so then they were selling that for heat pump couplings, heating the swimming pool. It's still it is the case. Okay. So yes, the experiments that we have done also at EDF with this, it was to couple the PVT with tank and to manage, to find scenario of managing the production of hot water during the day. So to fill the tank in terms of solar thermal during 2 hours, it was enough, and then to make the water used for cooling. So no connection to the tank anymore, and to cool the PVT in order to increase the efficiency of PV. Okay, we have also worked with Ankita on hybrid PVT application, more theoretically, adding some phase change materials. So the principle was to have PV cells and then add water channel, try to find good heat exchanger, and also to add a layer of phase change materials. So we have found that the addition of phase change materials is quite interesting for kind of using this as a dump. We can say that dump to stabilize the hot water production. Also to decrease a little bit the temperature sometimes and to increase the efficiency of PV modules. We work on water and also with air, and there was a paper made on this exploitation with classical electrical analogy modeling, but no confrontation with experimentation. Okay, a more recent one, so to see that there is still research on this in 2020, and it is an Indian, which has developed PVT with phase change materials and have analyzed by experimental and modeling. Okay. So this is two PVT. So there is one PVT with water, one PVT plus phase change materials. The phase change materials, he has chosen a temperature around 35 degrees. Could be 30. It depends on the ambient operating condition. And so he has compared. He has worked also on heat exchanger. As you can see, the heat exchanger, he said that it is look like a butterfly wing. I'm not fully convinced of the heat exchanger, but about the improvement of the wool collector, yes. Okay. Because you see the heat exchanger is like this, and this is going like this, and like this also, and this is going like this, thing like this. It looks like something. So you can see here the shape. So for such device, and as we have done also in the past, as I mentioned, you are obliged to compare what is comparable. Thermal energy is not directly comparable to electrical energy, even if the units are the same. You have to evaluate the content, the quality of this energy. You remember yesterday when Pankaj was giving some information about solar thermal efficiency. If you plot the solar thermal efficiency of collector, you will see that it is the efficiency here, sorry, it depends of a ratio depending of the water temperature minus the ambient temperature. Okay, so for a flat plate uncovered collector, you have a good efficiency finally when the water temperature is close from the ambient temperature, because it's a ratio. Okay, so this is becoming big. Temperature of water minus the ambient temperature is becoming big as a ratio. when the water is close to the ambient. But we don't, we have no use of water temperature which is at the ambient temperature. Okay, so that means that yes, of course, a flat plate uncovered has a good efficiency when the water temperature is going to near the ambient temperature compared to the other that will be like this. A coverhead will be like this, for example. But we are not interested by when the water of temperature is becoming close of the ambient temperature. That means that we don't give input in terms of thermal energy. Okay, so we are obliged to compare, and it is the reason why we are using exergy. So, in an energy point of view, we can say that we can add the efficiency of thermal plus efficiency of electrical. The power which is maximum generate, as you remember, the fill factor is equal to voltage for which the power is maximum multiplied by the intensity for which the power is maximal and divided by the intensity in open circuit. No, sorry, not in open circuit. Oh, in short circuit. Short circuit and voltage in open circuit. Okay, so that means that the power max which is generated for maximum voltage multiplied by intensity maximum, it is that. Okay, and so exergy allow to make a comparison between both of energy. It allows also to be interesting to see if there is a lack of exergy or not in your system. Okay, so it is this which is well seen and well used to when you have a system which is generate both two different energy vectors finally. Here it's electricity and thermal. Okay. So you can add exergy, thermal exergy, and electrical exergy. Thermal. Okay. And so I will give you a numerical application in order to have an idea of the value. Okay, so for thermal, what is a typical so I'm going too fast. So here, Q is energy. Hein? It's here, Q. MCP, so mass flow rate. So we will take a volumic mass flow rate of 1. In the paper, he tested 1 liter per minute to 4 liter per minute. What we can take as ambient temperature, we can take around 25 degree. It's 25 degree. Yes, it's a hieroglyph. And a typical so water temperature, we can say in the collector we can take 60 degree. With 25 degree outside, that means it could be around summertime. It could be possible. Or it's a bit high, maybe if it is uncovered. But we can reach, yes, between 50 and 60 degree. Okay. So I would like to have the thermal exergy, please, and then we will evaluate the electrical exergy. So this is water. In principle, it is the outlet temperature, but sometimes we can take the mean temperature inside the collector. So I will say it is outlet. So as soon as you have a value, you give it to me. Maybe you want me to remind you that Cp is cat dot 186 kilojoule per kilogramme per Kelvin. So the exergy has been extracted from the second principle of thermodynamics. So to achieve this kind of formula, you... Sorry? So I said TA is 25. And I say that I will consider that T water is around 60.
T water is the outlet temperature.
Yes, it's in principle is the outlet temperature. I just compute it between at midday, so I hope I have no mistake. With electrical, this is the area of the collector or the PV. This is irradiation. So typically we can say that for such a good day, the irradiation could be 800 or 900, okay?
TS is surface temperature of the sun. TS,
Where?
the second expression.
Ah, yes, here it is evaluation of the surface temperature. Yes. So what you will consider as a TS, for example?
6,000.
Hmm?
6,000.
Yes. I'm going to check that.
Doctor,
I'm not sure.
So, how much mass we are considering? 2 liter, 3 liter per minute?
What I said, I have made my for 1 liter per minute.
We need to convert LPM to kg per second. Of course,
You are obliged to use international. Yes, yes, every time.
we need the result. Don't ask
It is a number of modules, but we will consider one. Okay. No, and so what you will consider for TS?
6,000 kilograms.
No, it is not the. What did you take for TS?
Sun temperature.
No, it's not sun. It is surface of the module. Surface temperature of the modules, which is in fact usually the temperature of the surface of the cells, but because if you took the temperature of the sun, it's all the time negligible. So it's a
It will be very less only.
panel.
1 minus something. Value is always 1 minus something. It will be very less only.
Hmm?
Always 1 minus something.
Yes.
It will be very less only always.
Yes, we've got to check. We will say. I didn't compute it that. So if we consider ambient temperature, sorry, what I said for the ambient temperature, 25. So ambient temperature is 3 Kelvin. Yes. No, it's not 333. 333 is sorry, the water temperature. Wait, you imagine it is a W, and ambient temperature is 298 Kelvin. So do you have a value for thermal exergy?
351 total.
The total exergy?
How much is it? She got 351.
51? I don't find that. Which is your unit? Watt? Or kilowatt?
MCP decreased.
Kilowatt?
2 point something. 2.44 kilowatt. 2.44 kilowatt.
Maybe, yes. I didn't have the electrical one. Can you give the thermal one? I got the thermal one. Maybe first you can give me this energy.
2.4.
Yes, 2.4. Me, 4.5 or 4.9 you said?
4.9 kilowatt.
4.9, okay. Okay. So if you leave it like this, you should find around 0.26 kilowatt or 0.2 something. Hmm? I hope I will not make a mistake. I have to check. So, do you find the thermal around 0.26 or?
266.
Here? So 0.2?
685.
Okay. Yes, kilowatt. And I have a doubt about this. Oh, you have right. No, you are right. It is sun for this because we can find two formula. One like the thermal, so instead of useful energy, it is electrical energy, and one with the sun. I put it here. Oh. No. I thought I was put the. Sorry. I thought I put that. So the PV efficiency.
15% you can consider.
Yes, you can. I want just to give you nominal power is for the PV. For the PV nominal power is 260 watt. Efficiency is 15.78%. What do you need? So we can choose 800. Okay. Yes. No, you are right. It's not with this formula. It's not the it is. You can use the same formula with the PV electrical here, but here it is the sun. Yes, you are right. Of course. The surface of the sun.
Okay, what is summation of EDI?
Hmm?
EDI in the EX.
It is the complement, so it is what is lost in terms of exergy. We are speaking about efficiency, or it is called exergy destruction. So, did you find for the electrical, taking the sun temperature? Mm.
Area is also 1 meter square.
Yes, we can take.
Each module we are considering the
It's
same.
200 now. We can reach for this kind of power.
250 watt.
Yes.
One
So we can say 1.5. Yes. Okay. I think I've got. I was thinking to put it. Do you? Somebody has. I didn't have the numerical value. If somebody has a value, we can have statistical results. So if somebody give a value, we will see how many people have the same. Do you have it?
Actually, I will do this different. The electricity kitna hai? This efficiency is given. This is power. N is 1. Area is 1.5.
3?
Area is 1.5.
Yes, I took 1.5 square meter. 1? 177?
This will be 1.
It is
0.1 kilowatt. 0.177 kilowatt.
0.1. Okay. Okay, so it's a way to compute this. So after, it's just to show you how it is computed, and after he has also computed for all the data he find. He has managed to make the flow rate changing. Of course, the flow rate of the water circulation is a huge impact, okay, because you cool better the PV function, but you recover less heat because it's more fast, okay. So he finds that a good compromise was for flow rate of 2 liter per minute, okay. And he find that it was obviously I didn't take the word. And he find that it was obviously interesting to have phase change in order to have a gain in the efficiency of the electrical function. Finally, if you win in terms of electrical function, the global exergy efficiency is better, but you can find a compromise between thermal and electrical, and in his case, he find us it was a good compromise with phase change that he chose at 35 degrees in terms of melting, and with a flow rate of 2 liter per minute. Okay, so just an illustration to why in the field of PVT we are using very often exergy to be able to compare, to integrate both thermal and electrical point of view. It's not really my final support. Do you have any question? So very often there is thermal, electrical and economical analysis afterwards to see if it is interesting to use this kind of apparatus for both thermal energy generation and electrical. So we call that thermo electrico economical analysis. You will find that in the paper. So if you have no question, we can make a break before the second tutorial. Okay? We make a short break or we continue in the tutorials? Few minutes, maybe? No? Or
5 minutes maybe.
5 minutes? Yes. Okay.